So today we are going to have a look at the study heat conduction, and the spelling of the conduction is that. Okay, no I. Yeah, copy and paste from the first one, so I have to change in everything. Okay, now when we have a look at steady heat conduction, we will have a look at the concept of thermal resistance. We will have a look at the concepts of the limitation of thermal resistance. We will have a look at thermal resistance between compound shapes, between different materials. We need to have a look at uh, where the thermal conduction is significant. We will look at the insulation properties of the material, and if we got enough time, we will solve the multi-dimensional heat conduction problems using shape factors. Okay, next one. Now imagine we got a system here. Now in the system, the heat, this is a hot side, and that's a cold side. So the heat travels from a hot side to the cold side, and in the middle there is some conduction phenomena happening. So the heat will transfer to that, and then the heat from here, the solid, it will transfer to outside. The rate of heat transfer depends on what material is made up of, thermal conductivity of the material, and so on. One thing we need to understand is the rate of heat transfer into the wall minus the rate of heat transfer out of the wall is equal to the rate of energy change of the wall. So Q in minus Q out will be rate of change of energy of the wall with respect to time. So that's the dE of the wall divided by the dt. That's the differential, d over dt of the energy of the wall. If the heat transfer rate is quick, it means the wall is taking energy and expelling the energy from the system. Okay, so we got the equation for the steady energy equation. Q in minus Q out equals to d over dt of the energy of the wall. Now, let's say we got another equation for the conduction. Q in the conduction of for the wall, because it's solid, so conduction process happening. It's equal to minus Ka dt over dx, where T is the change, where T is the difference between the temperature, it's a temperature difference. A is the area of the wall, and K is the thermal conductivity of the wall. So K is constant, depends on the material. Now, let's say we got a condition here where there is a wall, and in the wall obviously there is different material. So there is a gap, maybe the material, that material, and the outer material is same, but some other material is in the middle. Now if we have a look at the temperature distribution, it has to be a straight line. The temperature distribution means if there is a hot temperature, the hot temperature heat will be conducted all the way to inside. Heat will go in and heat will go out. Now, according to the equation, if you want to find out how much heat has been conducted throughout, I can find that one through the integration, because then I need to look at each and every sector, and then I need to use the integration. Now, imagine the whole length starts from 0 all the way to L. The whole length is from 0 to L. So I will apply the integration when the length is 0 all the way to L, and I will integrate my previous equation. And then the temperature here is T1, but the temperature on the other side is T2. So temperature starts from T1, the hot, it goes all the way to the temperature T2. So here limit is with respect to length. Here the limit is with respect to the temperature. Because the K is constant, the A is constant, only the D is the differential. So differential, D is the changing one, so I need to put limit with respect to T. When you put the limits, K and A are the constant, they comes out. So this K and A, which is just the constant, they will come out. And now I need to apply the limits here. When I apply the limits here, that becomes the D2. Oh, sorry, Control Z. That one, blue. That will become a T2 minus T1, the upper limit minus lower limit, and the Ka outside, like that. Yeah, like this. Yeah. And then when you integrate that one on this side, the L will appear, because obviously there is no L. When you integrate, the L will appear, and this L I can bring it on this side. So that will be the formula. That will be the formula for the heat conduction rate. Q dot conduction is Ka T1 minus T2 over L, where the T is the hot temperature, T2 is the cold temperature, L is the thickness or the length, yeah, and A is the area, surface area, and K is the constant. Okay, now let's move to the next one. Now we got the formula. Instead of using the other equation, I just said like heat conduction of a wall is equal T1 minus T2 over R of the wall. What is the R of the wall? R of the wall, because before that here in this equation here, the equation was written as Q equals to T1 minus T2, and then next to that one was the Ka over L. Yeah, the L will all the way down. So that was the equation. Now this Ka over L, let's flip it over and let's call it R equals to L over Ka, and the equations become this, T1 minus T2 over R of the wall, resistance of the wall. So now we're going to use that equation. This is the thermal resistance concept. Now we know, according to the Ohm's law, I equals to V over R, I equals to delta V over R. So we can use that equation. Now if there is heat flow from the T1 towards the T2, T1 being the hot, the rate of energy flow equals to T1 minus T2 over the R, where R is the resistance of that one. If there is Ohm's law involved, I equals to V over R or delta V over R. We can use that one. This is if there is electric current flowing. Yeah, the top one is just for the normal wall. It just gives you the like comparison between both. Okay, moving to next. Now for the convection, I got R equals to 1 over HA. So that's for the convection we got. Now what we got for the convection, we got the equation here. Q equals to, let me write down. Q equals to M, Q equals to E sigma AS TS minus a T, and they have power 4, yeah, which is that equation here. This is a radiation, convection and radiation equations. You do not need to know these equations yet. Okay. So when we look at the radiation, the equation for the radiation R equals 1 over H radiation and AH. Now if I move to the next slide. So this is the equation for the convection, where A is the surface area and H is again the constant. Okay, now you can see here we got the thermal resistance and we got the H, which is the heat resistance coefficient. So H is the heat resistance coefficient, where T is the temperature of the surface and Ts is the temperature of the surrounding. The greater the distance, the greater the difference is, the faster the rate of heat transfer. It's also depend on the U value of the material as well, which is insulation property. Okay. H radiation depends on the temperature, while the H convection does not depend on the temperature gradient. If I want to find out the H, combined H, that will be H because of convection plus the H because of radiation. And H is the combined heat transfer coefficient. It's a combined heat transfer coefficient. So that's the heat transfer coefficient for radiation, H convection, heat transfer coefficient for convection, and that's a combined one. The unit are watts per meter square, Kelvin. Like watts because of power, meter square because we consider the area, and Kelvin because there is a change in temperature. Now let's imagine there's a wall and the temperature here is T1. Over a period of time, the temperature is dropping. If I have an instrument to measure the temperature of the wall here, I will get a reading. But as I go into the wall, the reading will drop until I reach here, because that's the temperature of the surrounding. Yeah. The greater the difference is, the greater the gradient. It will be, if the difference more, the gradient is going to be like that, more slopey. Okay, rate of heat transfer is given by the temperature of the surrounding, yeah, which is, sorry, temperature, the high temperature, inside temperature, minus the temperature of the surrounding, divided by the resistance because of the convection, resistance because of wall, resistance because of convection too, because there's a one convection happening here, yeah, the wall, that will be conduction, and then there's one convection happening here. It's exactly same as if you think about the value of the current flowing through the circuit, and then the total resistance is resistance, first resistance, second resistance, and the third resistance. So that's just exactly same. Okay, so you need to think that on both sides the convections will happen, both sides. Okay, now we got the thermal resistance network. If we are considering the steady one-dimensional heat transfer through a plane wall of, let's say, is the thickness L and the area A. So the thickness is L and the area A. We assume the thermal conductivity of the material is a K, and it's exposed to convection on the both sides. Now the higher temperature we assume is temperature 1, T1 is the higher temperature, and T2 is the lower temperature. The heat coefficients are H1 and H2. Now, for the process to happen freely, T1 should be higher than the T2. If you want other way around, that's a refrigeration, which means you have to pay the bills to get the electricity and do the work on it. This will do the work automatically. So if we have a look at the system, rate of heat convection into the wall is equal to rate of heat convection through the wall, which is equal to the heat of convection from the wall. These all rates are going to be same. We need to assume, we need to think that if the temperature of the difference is more, the gradient is going to be more, so that will be more slopey. Okay, now we have the equation Q equals to H1 A T1 minus T1, that's the outer one, that should be T2 here, yeah. And then we know this equation where I replace that with a constant. Instead of H, I just put that one Ka over L. So I just replace K over L. I put that one K over L. And that should be equal to the H2A, T2 minus TL, T infinity 2. This is the temperature of the surrounding. Oh no, that's supposed to be 1, sorry. This is the 1. This 1 temperature is here, and this is the temperature. So difference between that temperature and the difference between that temperature. Because the temperature here will be different than the temperature of surrounding, because the convection is happening, which means that surrounding is taking the heat from the wall and cooling it further down. Okay, so we got these equation. this equation, if I highlight,